Okay, thank you. Yeah.
Hi everybody and welcome to the CERIAS seminar. It is my pleasure to introduce today's speaker, Professor Xukai from IPY, and he is going to talk about weighted multi-secret sharing.
Thank you. Yeah, thank you. Okay, thank you for introduction. Okay, thank you for everybody coming. Yeah. So basically, I believe this is most are graduate students, right? Okay, that's nice. Okay, so maybe we can discuss a little bit in detail. Okay. Or also, if you have any questions, just stop me and ask. Okay. Yeah. Basically, the most part of this presentation is just one paper published in presented in ICCCN 2001 in August. This is some joint work, Edith Sabatino, Dr. Feng Li, yeah, and others. Okay. These are some outlines. For our graduate students, we took the security class, right? So we learned the secret sharing, right? How many we learned? Raise your hand. Oh, there's still quite a lot. You don't learn, do not know secret sharing. Okay, so let's briefly mention that this secret sharing. Then basically there are two types. Mechanism to implement secret sharing. We briefly discuss it. Then our proposed new scheme. Finally, it have some features. We'll give a discussion. Secret sharing. Maybe you heard an interesting story, right? The group of pirates. They have a map. This map. Leading to the treasure island, okay? Before they leave, who should keep, they need a slipper net, right? Who should be entrusted to keep this map, right? Anyone, take the map, maybe during the night, himself, went to that, island to take the treasure. Of course, cryptography, try to solve it. So secret sharing basically is a secret, a map, or simply an integer. Okay, an integer. Then divided this secret into shares. The secret can be unique, recovered from some set of shares. No information about the secret can be disclosed from other sets of shares. So typically, there is called a threshold scheme. Okay, so it's WN. Means the secret is divided into n shares. Any W or more shares can recover the secret, but less than W shares cannot. So weighted shares. This means the shares have different weights. A more weighted share needs fewer other shares to recover the secret. But a less weighted share needs more other shares to recover the secret. If the disclosed weight is W, as long as the sum of the weight of any subset of the shares is larger than W, the share in this subset when put together can recover the secret. Okay, as long as their weight, their weight plus together is larger than W. Multiple secrets. basically you want to share multiple secrets, not just one. Okay. Of course, one way to solve this multiple secrets is you use the secret sharing for one secret, then use multiple independent copies, right? For example, this Shamir game. This Shamir. Oh, I'm sorry. This Shamir scheme is the first scheme. It's pretty elegant. We will see it, okay? But it's for single secret. If you use multiple copy, you can get for multiple secrets. Also, people propose some others, such as this is for multiple secrets. It's much more efficient. Of course, here we have different combinations, such as single secret, same weight shares, single secret, weighted shares, multiple secrets, same weight shares, and multi secrets, weighted shares. Let's look at the first category, okay? Because basically we mentioned there are two categories, two typical mechanisms. One is based on polynomial and polynomial interpolation. Another is based on Chinese Remainder Theorem. So let's look at the Shamir scheme. Okay, Shamir scheme. In fact, this is we can see is a first secret sharing scheme. Here, suppose we have P is a large prime. Then the secret S is belong to ZP. Okay. There are two phases. One is shear generation. Another is shear recovery. Secret recovery. Let's first look at the shear generation phase. Of course, here we assume there is a central authority. Okay. He split the he keep the secret. He split it. Okay. Divided here. So select secretly choose W minus 1 random elements of ZP, A sub 1, A sub 2, A sub W minus 1. Okay. Here we suppose the weight. Okay. W is a weight. W is a weight. Then construct a polynomial in ZPX. ZPS, as if you look at this polynomial, okay, it's just AXI times x power I, then plus together. Okay, this I from 0 to W minus 1. When I is 0, so this A0, A sub 0, this constant term is that secret. Okay, is what you want to share. Okay, what you want to share. Then choose undistinct non-zero elements, xi, xi. Of course, here suppose this I from 1 to n, we design n shares, Then compute yi is axi, axi. So this xi, yi is one share, okay? Xi. This basically is a point, right? Is point on this polynomial. But this polynomial, the degree is W minus 1. W minus 1. In the secret recovery phase, so any W or more participant can pull their share together. You get n points, right? Get n points. They can recover the polynomial. Recover this AX using polynomial interpolation. The easy way to think about it is this: if you look at this polynomial, is right. Basically, you have A0, A1, A2, A W minus 1, right? You have W unknown, W unknown. If you have W points, then you can establish n equations, W equations. Then you can solve the W unknowns. So as a result, they recover this AX. Then S is A sub 0. S is sub 0. So they recover the secret. But any group with less than W participant, they cannot. Of course, if we want to use it, suppose the share is weighted share, means some share has more weight, some share has less weight, right? And of course, you can, for this Shamir scheme, we can use what? Suppose the weight is pi, then pi points are computed. So this pi points as one share. Because you have more points, you have more weight, right? Oh, I must stand here. So this I cannot use this one, right? That's okay. Okay, sorry. Okay. Let's not. So you look at that one, okay? Because I pointed this, maybe I can use this one to point it. Okay, that's my bad. Okay. Any questions so far? So here we give a concept term. It's called base bit. The number of bits for integers in this Shamir secret scheme. Okay. Basically, this base bit is log p. Okay, log p, such as 196. Let's look at another mechanism. It's based on Chinese Remainder Theorem. Okay. How many, we should have learned Chinese Remainder Theorem before, right? How many know it? Not so many? How about this side?
Not everybody do cryptography here.
Oh, okay. So, okay, that's good. So we discuss it, okay? So suppose N1, N2, Nr are pairwise coprimes, then let N is a product, okay? The product. For any given integers A1, A2, AR, consider the following congruences. X is A1 modular N1, A2 modular N2, AR modular NR. Then this system has a unique solution modular N. This solution is this AI times NI times YI, then plus together. Because we have all this A1, AI, right? What is NI? NI is this big N over N sub I, big N sub I. Okay, and this YI is the multiplicative inverse, okay, multiplicative inverse of NI modular big NI, okay. So this, if you have these congruencies, you can uniquely recover X. Of course, on the other hand, give X, it's easy to compute this one, okay? Compute each AI. Okay. So, of course, this computation is also efficient, okay? If you have this, this equation, okay? So, this is a typical scheme, okay? It's based on a Chinese Remainder Theorem. Okay? It's called Mignotte scheme, okay? Mignotte. At first, it defines this Mignotte sequence, okay? Mignotte Kn Mignotte sequence is a sequence of positive integer. Okay, here such that pi pj is equal to 1. Basically, the same as they are coprime, okay? Coprime. Because the coprime means that GCD is 1, okay? GCD 1. Then this condition, okay? This condition. Basically, this condition means the end k minus 1 number, their product, is less than the first k number, their product. Okay, the product of first k numbers. Because here is from Pn minus 1. Okay, here is to P1, P2, Pk. Okay. Then, given a public known Kn Mignotte sequence, the secret S is chosen as an integer in this alpha beta. Okay, basically this first is alpha, the second is beta. Okay, this S is chosen between this alpha and beta. Okay. This is secret. Then what is the share? Then each share, SI is this is the secret, just the modular PI. Modular PI. Of course, this share you mean is the PI and the SI is one share. Okay, PI and SI is one share. Basically, you can think of this is a share generation phase, right? Then in the secret recovery, given k distinct shares, you build this congruencies system. Then use Chinese Remainder Theorem. This X is recovered. Okay, this X is recovered. Because this condition, okay, this S is between alpha and beta. So if you have k shares, okay, k shares, because this alpha beta condition, so this k share, the product will be larger than beta. Okay, will be larger than beta. Okay, as a result, this X is a S. Okay, as a result, is recover the secret. Recover the secret. So this is a Chinese remainder based. But if less than k shares, you will not. Okay, you know, because this condition is very important. This condition. So, any questions so far? No. Okay, that's great. So let's look at a new, new scheme. Okay, new scheme. So a new CRT based, weighted. Here you can see this one is does not have that weight. Okay, it's just for single, same weight, same weight. Here we have let's see where we have that observation. Here, basically from here, we have the observation. Okay, observation. The observation means if the weighted share, right? Weighted share. If your weight is pi, okay, weight is pi, then you have pi points, right? You have pi points. So basically here, suppose means the base bit is this much, then for this weight, this share with this weight, here the beta for this share is this pi times 196, right? Because if for each share, if for the weight 1, the share is this 196 bits. If here the weight is pi, then it should be pi times 198 bits, right? It have this pi points, okay? So based on this observation, this you can think is a direct relation between this weight and the length of the share, okay, and the bit length of the share. Okay. Then we propose this one, okay. Assume W, here should be a small w, okay, small w. W is the disclosed weight. Then N is the number of bits for the base number that basically that base bit, okay, the base bit. Of course, this W we assume is less than N. Normally, W is much less than N, okay, because W is disclosed weight, okay. So, as a result, the secret S will have W times N bits. W times. If it does not have these so many bits, it just randomly expand it, so that it have W times N bits, okay. Then for user UI with the privilege pi, we select the prime pi, which have pi times N bits. Okay, we select the prime pi. It has pi times N bits. Then we compute this S modular pi. S modular Pi. Then this Ri Pi, S modular Pi and Pi as a share. And of course, this share has a weight Pi. This one share has a weight Pi. So this you can think is share generation, okay? Then in secret recovery, we know for any pool of users, suppose U1, U2, UE, as long as their weight sum of their weight is larger than W, then we have this congruency system. This system will recover S. Use the Chinese Remainder Theorem. As long as their weight, okay, sum of their weight is larger than W, then this will be recovered. Because as long as their weight is larger than W, this is P1, P2, PE, they time together, their product will larger than S. Okay, will larger than S. Because here is what does it mean? Okay, S has Wn bits, but this P has at least this much. Okay, and this much. So this P is larger than S, then it can be recovered. Okay, it can be recovered. Any question with it? Okay, I hope we quite slowly. I hope you can understand it. Okay. So some discussions. We can reduce the condition is larger than W to larger or equal to W. But in this case, we need to introduce a help. Because there's the possibility, even each one is because when they time together, it could minus the E base. Okay, it could be minus. For example, if 1000 is 4 bits, right? Another 1000 is 4 bits, right? Then the time together is not 8 bits, okay? Right? It's not 8 bits. It's 6 bits. It's 7 bits. It's 160. So that's the possibility. And that's why if you reduce the condition to this larger than equal, you may need to introduce a help. Okay, this help. This helper, whose modular is the smallest prime of W base, and whose share is this much. Okay. When this helper is incorporated into that congruence system, then it can be recovered. Of course, you will read the question. If this one is publicized, of course, it reduces the security strength a little bit. This is depending on how to use it. Okay. So, in addition, here we assume Pi are primes. In fact, pairwise coprimes are enough. For requires prime, it's just because the Chinese Remainder Theorem does not require that prime, right? We know if that prime, of course, they are all coprimes, right? It makes the life easier. But the coprimes are enough. One wonderful thing is that this scheme, okay, can be basically you can adaptive to all 4 cases. We said there are 4 different combinations, right? So the sharing of multiple secret, okay. So previously, even we mentioned is share single secret. It's easy to extend to multiple secret. Suppose we have k secrets to share. Each have n bits. We can easily extend the newly proposed CRT scheme to produce a weighted multiple secret sharing scheme by simply concatenating the secret together to get a k times n bits secret. If you have a multiple secret, you just concatenate them together to get one secret. Of course, there are 3 cases to consider. Okay? One is this k is less than W. W is disclosure weight. we need to append random base to get W times n base. Okay. If k equal to W, do nothing. Do nothing. If k is larger than W, in this time we may need a help. Okay, we need a help. Of course, once the concatenated secret is recovered, you can split it into these multiple shares, multiple secrets. You get back. Any questions so far? Okay, of course, the security basically is based on CRT, is similar to Mignotte scheme. In terms of time complexity. Let's see. We'll suppose n is base bit, W is disclosed weight, n is number of shares, P1, P2 pin are share weights. Okay, this is the big W is this PI plus together. Okay, the sum of PIs. Okay. So we compare with Shamir scheme and our own scheme. So we get for the share generation and the secret recovery, the new scheme is this much. Okay, is this much. But for the Shamir scheme is this much. Okay, is WN squared. For our scheme is n times log W log Wn log W. Okay, log W. Okay. Of course, our people give us some detailed analysis. Okay, how to get this value. The secret recovery. This is a new scheme. This is Shamir scheme. Of course, here the complexity in terms of bit, how many bit operations. Okay, in terms of bit operations. For the we will compare our scheme with this McNulty scheme. Okay, McNulty scheme. The difference is between this generation. Okay, generation of this modulus. Generation of this modulus. Because for computer share and cover secret recovery, they are same operation. But how to generate this modulus? How to generate modulus? So McNulty scheme is a little bit higher. Our new scheme is a little bit fast. It's a little. Also here, when PI is equal to 1, this means same weight. Okay. If same weight, this is W equal to n, then they are same. Okay. Yes. But for the weighted share, okay, for the weighted share, generally this W, here is W, okay, here is W. W is this is PI plus together, okay. This W is larger than n, okay, larger than n. It's possible, okay. Then our scheme is more efficient, okay, more efficient than McNulty scheme. Yeah, nice. So here is some experiment. So if you look at this figure, this is a comparison, okay, between this new scheme and Shamir scheme. This red line is a theoretical line. Then this dotted line is experiment. So you see this is a Shamir scheme, theoretical experiment. This is new scheme, theoretical experiment. This is the share generation, okay? Share generation. Here you can see this is the size, okay? Size of secret in terms of bits, how many bits. This is how long it takes to compute these shares. Here, suppose disclosure weight is 8, 15 participants. The number of secret is 1. In terms of secret recovery, of course, we consider single secret, single secret. So you still look at here, this is better, okay? New scheme is better. So this is secret size, this is secret recovery, secret recovery. Let's look at the single. Okay, another measure is for different closure weight. Okay, because previously we assumed this disclosure weight is 8. Okay, in terms of different disclosure weight, So this disclosure weight is from 4 to 14. 4 to 14. Suppose it's still single secret. You can see this is Shamir scheme. This is the new scheme. Let's look at, okay, this is recovery, okay. We have a similar result, basically. Let's look at these multiple secrets, okay, multiple secrets. Multiple secrets, we made some test, experiment. We can see, the new one is still better than, the old one, Shamir scheme. This is the secret recovery, Let's look at another one. Is for comparison with okay, this is with McNulty scheme, okay, McNulty, because McNulty scheme is based on CRT, right? We mentioned, So, in terms of shear recovery, secret recovery, they are same. But the question is the modular generation, okay. In Shamir scheme, in Mignotte scheme, the shear modular generation is take much more time. So here, you use a modular generation. Here is what we get. Here we have theoretical, we have experiment. This is McNulty scheme. This is for weighted shear, okay? This is for weighted shear. This is for same weighted shear. This is for weighted shear. We can see it's still better. Here is some any questions? Okay, here is some experiment. Some just one program running, it print out something, print out something. Some snapshot. If you give disclosed weight W is 4. And is 64. Suppose we have 6 users. They have all weight 1. If you have secret this, okay, this is so these 2 lines, 1 secret. So user 1, user 6, they all have their own shares. Okay, this share, one is at RI, one is at PI. Okay, that is that modular. Okay, that modular. Modular and this. Okay. Now here the helper. You see the helper is very small. Okay, is 211. So if user 1, user 3, user 5 put their share together, you recover the secret. Okay, recover the secret is this much. Okay, this secret of course is not this secret. Okay, not secret. It's wrong. Because we know that is what we expect, right? And because their weight is 3, but the disclosure is 4, so they cannot recover it. Here, if we use user 1 and user 4, user 1 to user 4, if they pull together, then you can see here the secret is recovered. Okay. The secret is recovered. Of course, this is what we expected because the weight is 4. Okay. Please remember here, this one we use a helper. Okay. This helper even so small. Okay, but it's so important. Okay, so important. But if we don't use this helper, then you get wrong. Okay. Of course, this helper is only used for when the sum of the weight is equal to W. Okay, if you want to recover it, then you need to use this helper. Of course, if your sum of weight is larger than the W, then you don't need help. This depending on how your scheme works. Okay. So here is the snapshot for multiple secrets. Suppose we have 3 secrets, 0, 1, 2, 0, 1, 2. Then we combine together, you get this one. Okay. This one and this one is not, because this one is in what? Is in decimal. Okay. So when you combine this one, please remember this one needs to be 64 base. Okay, 64 base. If you in the computer is binary, right? In binary. So that's why it looks like this one is not the concatenated of this one. In fact, it is. Okay, it is because it's in binary. It's a binary concatenation. Okay, binary concatenation. So this is a combination of these 3, just concatenating. So if you look at, suppose we still have 6 users, their weight are 1, 1, 1, 2, 2, 3. Okay, this is a different weights. Okay, they have a different weight. So you get these shares, different user, different share, because you have a different weight. Okay, here you can see this. If your weight is larger, of course your modular is larger. Okay, because if you is pi, then pi times n base for your modular. So you can large. So here is user 6. Here the helper is 11, 8, 11. So if user 1 to 3 pull their shares, its weight is 3 is less than 4, so the recovered secret is not correct. Okay, not correct. Of course, the recovered combined secret is not correct. Then when you split it into 3 shares, it's not correct, right? When you split it into 3 secrets, it's not correct. Similarly, if you have this user 1, user 3, user 4, since user 4 has weight 2, user 4 has weight 2, so user 1, user 3 each have weight 1, but their sum is 4, right? Sum is 4. As a result, they can recover the secret. Of course, in this case, you generally need that help if your sum of weight is equal to disclosed weight. If you don't have this helper, sometimes you can recover it, sometimes you couldn't. But with the helper, it always recover. Okay. So this is another example. Let's skip it. Okay, let's look at another fine-tuned shares. Which allow non-whole number weights. Okay. So basically, all the existing scheme. You we mentioned this McNulty scheme and Shamir scheme. In fact, there are quite a lot. Okay. There are many, but they don't. They still these these 2 categories. Of course, they discuss many different features, such as remarkability, dynamicness, verification, something like that. Because when you the dealer, okay, who created a share, he can give a user a false share. Okay, when a user pull his share, the user can give a false a forged share. Because he want to cheat. Okay. Anyway, but they don't they're still based on these 2 categories. Okay, all the existing shares, they deal with share weight as a whole number. Okay, as a whole number. Right? Your weight is 1, 2, 3, 4, or whatsoever. Then its share will have pi times n base, where n is base. But this new CERIAS scheme can allow share weight to be non-whole numbers, such as 1.5, 2.5, etc. Okay, etc. You don't need to be whole numbers. So, but here, but the share, each share will have this much bit, okay, this much bit. Not no matter what, this of course this pi maybe is not what, maybe not a whole number, okay, but we generate is modular is pi times n seeding, okay, seeding. We generate a prime with this number of bits. So even this pi is not an integer, it's okay. So as a result, we generate a share same as previously, but the modular is have this much bit. This much bit. So similarly, for a pool of share with this weight, okay, with this, as long as the sum, the Pij times n, their sum together is larger than W times n, then the secret can be recovered. Secret can be recovered. Otherwise, it cannot. It cannot. Of course, this allows, as we can see, right? This allows users to have fine-tuned privilege. Privilege. Also, this allows the different requirements. It allows this scheme is fit to different requirements and constraints of various devices. Such as sensors, PDAs, cellular phones. Because these different devices may have different computational capability, right? If they are less capable, you give a less weight share, okay? Less weight share. If it's capable, you give more weight shares. Okay. Any questions? So basically, this allows this scheme is applied to more, broader field. Okay, broader field. Of course, here I give a few examples. So here you see we have this 1.1, 2.2, 3.3, 2.5. Okay, right? We have this kind of shares. Different weights, even non-integer weights. Then if you do it. So user 1 is shares, user 2 is shares, user 3, user 4, user 5, user 6. Okay, this helper is 1312. Okay. If user 2 and user 6, if they want to recover the secret, if they pull their shares because user 2 the share is this, user 6 the share is this, then the recovered secret is this one. Okay, what is the secret? The secret is this one. Okay, it's 1127 something like that. Okay, then its recovered secret is 1477. Okay, of course which is wrong, right? Which is wrong because the number of bits covered by these two users is 237. Which is smaller than number of bits for disclosed weight, 256. So you cannot recover. Okay. Of course, if we have this one, user 1 is 1.1, user 5 is 3.0, the secret is recovered, okay, the 1127, etc. Okay. Because you see their weight, right? The sum together is 4.1. Is larger than 4, so this is recovery. So I think here the brief summary. New CRT based theoretical secret share scheme. As you can see, it's pretty simple, right? In principle and efficient in complexity, in implementation. It's generic and flexible in supporting all 4 secret sharing schemes. All 4 schemes. It's fine-tuned in weight and flexible in supporting various devices with different computational capabilities. So it's efficient in Shamir and McNulty scheme in shear computation is more efficient than Shamir scheme and as efficient as McNulty scheme in secret recovery. Okay, here because it's in shear computation, okay, we mean that this McNulty, the shear generation it including that modular generation, okay? Because this McNulty scheme is modular generation is take longer time than new scheme. Of course, it's possible you have some extensions extended to deal with some other desired features, such as dynamicness, variabilities, study the application to real-world applications, such as secure e-voting. So these are some references. Of course, if you these people already published it online, you can if you want to look at the detail, because this 2001 is in August. Okay, in August. Okay, that's it. Questions? One thing I want to mention a bit is these two categories. There is in terms of security, there is a difference. And Shamir scheme is called perfect secrecy, right? If you learn this unit, it's perfect security, which means if you have this, such as this Kn, right? Okay. If you have K or K plus 1 or more than K shares, you can totally recover the secret. But if you have less than K shares, even you have K minus 1 shares, you have no bit. You do not have any bit of information about this secret. It's called perfect secret. If you have K minus 1 shares, any value could be a secret in terms of this K minus 1. You cannot, there's no way to determine which one. But this Chinese Remainder Theorem based, as you can see, is not perfect. Because when you have more shares, right, you are closer to that secret. That secret. So here, for all the Chinese Remainder Theory, it has this assumption, okay? Which assumption? Here we have this alpha beta, okay? This alpha beta. It assumes this beta minus alpha over beta is large enough. Means, you try this one, try that one. There are too many tries. You cannot, is large enough. Beta minus alpha over alpha should be large enough. So of course they give another name. For some specific case, they have this called asymptotic perfect secrecy. Okay, asymptotic, but it's not perfect. Okay, not perfect. So it's pretty interesting, okay? It's some theoretical stuff, okay? Okay, I think, time is pretty close. Any question? Okay, thank you. Yeah.